Can you not?
Hi, Christy.
Hi,
Jack
Christy.
and
And
Heather.
Heather and Jack.
And anyone reviewing.
And us? Yeah, probably me later.
Happy Thanksgiving. Yeah.
Welcome to the back bus.
Future.
That's right.
Try to do some non-side soil grass.
It's weird as that chapter.
Log Are you allowed to All right, here we go. We're going to continue with our notes. I think we had some more challenging ones, correct? That we had filled out?
Yeah. Most of them.
Yeah.
We stopped at
Right. Okay. I would like, is the very last part of your packet empty? Like the last page, you know?
Yes.
Yes. Okay, so I want you to put a line across. And I want to do some challenging domains really quickly. How about we do find the domain, just to warm our brains up a bit, of f of x equals 1 over sine x, which is nothing more than cosecant, right? But let's use our domain, dangers or gotchas to figure this out. What would it be? We would say sine x not equal to 0. Well, when is sine x equal to 0? 0 and pi. So we would say x not equal to
0.
pi n. Okay. Got it? So, and we could know that this is equal to cosecant, and we remember how to graph that really quickly, right? How do we graph that? Cosecant. You graph the underlying sine function. This is our little mini review. And sine starts on the midline with our critical points here. And then when will we put our asymptotes? At 0, right? And every pi n. And then our graph would look like this. And if we wanted to state what the range was, so we would say the domain here, this is how we would write it, all reals not equal to pi n, and an element of the integer set, and then the range, what are all the possible values of y? Good. Whoops, -1 inclusive. Union to infinity. That's not too bad. So what about this one? This is going to be f of x equals we do. How would we do that? We would say that sine x plus 1 has to be greater than or equal to 0. what is the 0 there? Right? When is sign equal to -1, right? Because that would make that 0. Okay, so x would be 3 pi over 2 plus 2 pi n, n-e-z. And since this is an inequality, we're going to do a sign chart. Ooh, you're like a sign chart with a sign function. No. So what are the zeros? We say 3 pi over 2. That's got a 0. Because we're going to add 6 pi over 2, which, no, 6 pi over 4 pi over 2, right, which would be 7 pi over 2. Let's go to the left. Negative pi over 2. Nice. Now, if we were to superimpose this graph, where's the midline in your mind? Remember, this is 0, right? So it's up here at 1. So what's this curve doing?
Well, it starts at the midline.
Starts at the midline.
It's all
If it's positive, it'll go upwards.
Right. So it's probably doing something like, because this is going to be its low point, isn't it?
Would it not be hitting the midline at 3 pi over 2?
I'm sorry?
Why would it be hitting the midline at 3 pi?
Why would it not be hitting the? Well, we decided it was equal to 0 when x was all of these points, right? And this is y equals 0 if we're doing a sign chart. So this is going to be plus, 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 plus. All real numbers.
Will it always be that way?
Well, I mean, for this one. So the domain here is negative infinity to infinity. And the range, the midline's 1, the amplitude's 1 under there. Square root of 1 is, the max of this is going to be 2. So the square root of, you root that. All right. What are we going to do?
You want to graph it?
We're going to graph it. I don't know how to get rid of that. Okay, we're going to graph it with Desmos. Square root. Y equals, yep. Sin x plus 1. Can you click on these, the zeros? Can they match our sign chart? Nice. Did we just do some analysis on domain that was different than at Honors Algebra 2? We amped it up a bit. Ooh, wow, really big. All right, I want to go back to that graph. Okay, now let's see what the max is, shall we? Because isn't that another interesting point? What was the max? Click on that. What is 1.1414? I'll take a guess. Wild guess? Square root of 2. So the maximum is square root of 2 because the maximum sign will be is 1 and 1 plus 1 is 2 and you take the square root of that and you get root 2. Got it?
Why is it 1 plus 1?
What?
Sin x can be as 1. Oh, because it's sin x plus 1.
Yes, right.
Okay.
Good. All right, another interesting one. I'm going to keep it with sine here. What if we just do something basic like right, so we're going to say sine x has to be greater than or equal to 0. Okay, do we know when it's 0? Pi n, right? We just saw that up above. So let's do our sine chart here. At 0, at pi, at 2 pi, we have zeros. And I'll put a negative pi on here, just for kicks. Now, what do we know about the sine curve?
It's not gonna go through because it's
Right, between 0 and pi, think about that. In the first two quadrants, sine is what? Positive. So the first part of the sine curve starts on the midline, right? It goes like this. And then what happens? And then it goes up again, and then it goes down on this side. And then up again. And remember, the sine chart, that's always y equals 0. Okay, so how would I write that domain? Because I can only take the square root of the positive y values, correct? Yes, what are we going to do? 0 plus how far to the next interval? Plus 2 pi n? N EZ. Now, is this going to be an open or a closed bracket? I messed up, didn't I? That should be a closed. Yes.
Why would it be 2 pi n if it goes below?
Okay, I'm saying my intervals are going to be, I'm starting at 0. When do I hit the next interval where I have positive numbers? Here, right? And that's 2 pi away. Wait, well, let's do where does the first one end? Pi. Plus. So what I'm trying to do is highlight this interval, and any interval. How far apart are these intervals? Right? So we're going to say this is 2 pi n. Does that hit every interval? Harrison, you okay with that? Yeah? No?
Why is it pi plus 2 pi?
I'm sorry?
Why is the block the black one
Okay, so when this interval is 0 to pi, I think everybody in the room would say this interval, and I'm going to break this off. This interval would be 0 to pi. Do you agree?
Yes.
What's the next interval? Let's write the next interval.
2 pi to 3
No? 2 pi to 3 pi. I mean, I could write a whole bunch of intervals, or I could say
0 plus
0 plus every interval that's 2 pi away from this interval.
Okay, yeah, I
You
understand
see?
that part. So then the second part of the domain starts at pi because you're going to negative.
Yes. Got it? Yes.
Would you not need the sum between them too?
No, why can I take the square root of those negative numbers? The answer is
No, just like in between 0 and pi. I don't understand how like that's.
what is n? Okay, so let's say n is 0. What is your interval? 2.
Are you the decimals, please? Like n is 0.
Yes.
Be 0.
Let n equal 0. You get 0 to pi. That's the first one. Let n equal 1. 2 pi. Ah. You see how that's covered?
Yeah.
Just one.
Yes.
Do you only do the square root thing on the ranges?
Yes. Yes. Okay, now let's do a slight variation. And let's say I do f of x equals 1 over root sine x. What's the only change? Okay, yes, it's on the bottom, but
Sine x is not.
can't equal 0 now, so it's going to be the same thing except open brackets.
Sure.
I knew that's what you meant. Everybody got that? Because you can't include them now. So this would be the domain, 0 plus 2 pi n. Those are kind of fun, aren't they? Yeah, I think so.
Range is.
The range is going to be weird, I know. But we could do the range on the calculator, right? So let's do this. Can you, we're going to do the Desmos here for these. All right, let's do the square root of sine x. See how it looks a little strange? But we knew that. 0, 0, pi, pi over 2, 1. If I were to make this 2 sine x under there, what would it be? What would the max be? No.
Root 2.
Root 2. You see? Because the highest thing sine would be is 1, and then you'd have root 2. Okay, so take the 2 out. So, all right, that's so we can, I can make a little snapshot of our, oh, and then let's click on our, I'll do it because I'm right here. Thank you. You're like, Mrs. Muller, we're going to start taking square roots of these things. Oops, I want to put this with the other one up here. So, and then we're going to, then we're going to do 1 over the sine. Can we do that next? Hang on, let me get this down. One divided, of course. Ooh, that looks wild, doesn't it? Let's click the bottom point. But we knew it was going to have asymptotes, didn't we? Because it has a denominator.
So wait, do you want us to know how to graph that?
No,
Okay.
no, gosh, no.
So you just need to know how to do like.
But we knew it was going to have multiple asymptotes, right? Multiple asymptotes when sine x is 0.
Is that the same thing as root cosecant x?
Let's see if it works. Can we, may we, using the properties of radicals, rewrite this as this?
Yeah.
Yes? Which is equal to, we can rewrite it like this. Which is equal to. Yes, it is. But I just wanted to not freak anybody out and just do sines today. And you notice what part of the, excuse me, the cosecant graph are we missing? We're missing the negative pieces. Because you can't take the square root of the negative ones, can you? Because
Yeah, then you just cut it off.
kind of fun. All right. Moving right along. Here we go. Continuity. Now, this is, I hope, going to be nothing new. gonna make it smaller so I can have it all on one page here. Continuity in math is just in its most basic form. When I put my marker on the board and I start drawing my function, I don't lift it off the page, okay? This one here is continuous for all x. Does everybody make logical sense out of this? This is a quartic. This is, believe it or not, that's an open dot. If you would draw an open dot there. Now, don't be that guy or girl that says, Mrs. Muller, I can draw that without lifting my pencil off the board. Watch.
No problem.
But is there a spot in the domain that's missing? Yes, this is called the removable discontinuity. It's like we just took and removed a single point. Now, how do we come up with those functionally? Where is this discontinuity? This discontinuity is at x equals at 1, or is that at 2? Can you read it? It's at 1?
Also,
Yeah, it's one.
Okay, what is the equation of that line? Anybody? Is that x plus 1? So you could say, if I were going to come up with a piecewise for this, that it's x plus 1 when x is greater than, I'm sorry, I have brain senior moment there, ha ha ha. When x is greater than 1, right, and you can say this is x plus 1 when x is less than 1, and we leave the open piece there, right, the open domain. Now using limits, do we remember limits? I could say the limit as x goes to 1 from both sides. What does it look like that is? Everybody agree that it's 2? Is that equal to f of 2? No, why? Here's your right.
F2 is 3.
No, f of 2 is,
yeah, I think it was 3.
You mean F of 1?
I mean f of 1. I'm sorry, you're right. I'm too excited, right? That's f of 1. Well, oh, right. This is, we say this is what? 2? This limit is 2. That's the y value we expect to reach when x is 1. But this is, f of 1 is, does not exist. So this is no. That's why it's not continuous. If the limit from the left and the right does not equal the function value, then you will have no continuity. All right, let's talk about the Jaf discontinuity here, which is down here. Another piecewise. Now, one of these is supposed to be open, so I'll let you decide which one's open. The bottom? It's not a function, right? If one of them is not open. All right, Jaf discontinuities. That's when the y's are changing. You see removable, does the y change on the left and the right? On the Jaf discontinuity, what happens on the left and the right? The y's are dramatically different, okay? Infinite discontinuity means you're approaching some kind of infinity on the left or the right of the vertical asymptote. You guys are familiar with these? Yes? Moving right along. Function is increasing from left to right. Yes, ma'am.
Real quick for the infinite discontinuity, is it just like reaching an asymptote?
Yes. Increasing from left to right means your function is, your y values are going higher. Decreasing goes from left to right. Your y values are going lower. If you are constant, you are not changing your y value. Everybody got that? Nothing new. Oops. Did I mess it up totally? Yes, I did. Oh. Here we go. Extrema, we know about these things. We've heard about them before. Local max, local mins are in their neighborhoods. Are they the highest spot and the lowest spot? And they are Y values. That's the biggest deal. Extrema are Y values. Absolutes happen to be the highest Y value possible and the lowest Y value possible. Are absolutes also local? Yes, because in their neighborhoods, are they the highest spot? These are also local. This function is increasing. I want the x intervals where this function is increasing. This is A, this is 0, and this is D. So moving from left to right, what are the x intervals the function's increasing? From negative infinity
To A.
and
0 to
0 to D, yes. Function's decreasing, A to 0. And the function's constant from D to infinity. Now, when I do increasing and decreasing intervals, I do not use inclusivity, brackets.
Don't do the in-union one.
You can if you like, questions on that? This function has a maximum where? What is the maximum? E. Max of E over what interval? D to infinity, right? Function has a local min where? At 0. What is its value? Min at, of C. X equals 0. Okay, have a happy Thanksgiving, okay?
Thank you.
Yeah.